Good day, ladies and gentlemen. How are we doing? Just wanted to let you know I am working desperately on getting Google Meets to work on my computer. I was having good luck with Zoom, but the district shut down Zoom because of Zoom bombing. So as soon as I get this Google Meets working on this computer, we will have some live class sessions for those kids worried about taking, or those kids taking the BC test. Today I'm going to talk about differential equations and Eulers method. What I'm doing, I have access to many practice AP problems for this year, or a few, but before I hand out those, I want to review some basic BC topics that we've done earlier in the year before I do a whole free response particular question that's available. And today, along the same veins as logistic, because last week we talked about logistic differential equations. Today we're just going to talk about differential equations, and we're going to talk about this thing, Eulers method. And I don't know if you remember Eulers method, but Eulers method is a pretty straightforward topic, pretty straightforward BC topic, may or may not be tested. I would think that there's going to be a part of an AP problem that uses Eulers method. So I'm going to start this off, this particular video, using Eulers method. So here I have a differential equation. This particular differential equation here, this particular differential equation is what we call, this is non-separable. So I cannot solve this differential equation because it's not separable. So what I'm going to do is I'm going to use Eulers method, and I'm going to estimate the y value when x is equal to 2, knowing this initial condition up here that y is equal to 3 when x is equal to 1. Okay, so y, and I can, sometimes they use this notation, y of 1 is equal to 3. That means 1, 3 is on this curve. I cannot call this curve a function, but it is indeed a curve. So here we go. We're going to use Eulers method to estimate the y value when x is 2. And what we're going to do is we're simply going to use only 2 steps. You're not going to be required to do many more steps. And in a normal testing year, rarely have I seen College Board require more than 2 steps on Eulers method. So we're going to use 2 steps, Eulers method with 2 steps. And the steps are going to be of equal size, of equal width, so what I'm going to do then, I realize whatever my graph is, I'm starting with this point right here, 1, 3. Starting at this point 1, 3. This point right here is 1, 3. And what I want to do is I want to estimate this y value when x is equal to 2. This is the creature that I want right here. I want to know that. And I'm going to use 2 steps. So if of equal width. So if I go from 1 to 2 in 2 steps, and these are equal widths, this is equal to that, this midpoint right there is going to be 3/2. Okay, so I'm going to start at 1, 3. And here, how do you use Eulers method? I'm simply going to create 2 tangent lines. This will be a good, I'm going to come up with 2 tangent lines. Euler's method uses tangent line. It's another way to do tangent line approximation. Okay, so I'm going to go tangent line 1. Tangent number 1, and I'm going to call it tangent line 1. And I know that the equation of a tangent line is the output. I'm going to do the tangent line 1 at this point right here, 1, 3. And so we know a tangent line is going to be the output plus the derivative at this point 1, 3 times x minus 1. That's simply a tangent line. We've been talking about tangent lines a lot since the beginning of the year. So all I need to know with this equation is what is dy dx at 1, 3. Well, let's not forget that dy dx, what was dy dx? I'm just going to rewrite it here, so I have to keep sliding up. Dy dx was simply equal to x plus y. So to find this, 1 plus 3 is 4. So tangent line number 1 is going to be 3 plus 4 times x minus 1. That's the tangent line 1. And this tangent line, to demo that tangent line is go right there. But I'm going to stop that bad boy at 3/2. So what I want is this first point. Well, I want the second point. I'm going to create a new point by evaluating the first tangent line at 3/2. Alrighty, so let's do that. Let's extend the page down here a little bit, please. Okay. And so what I want is I want this first tangent line at 3/2. Because I want to find this point right there. Plus 4 times 3/2 minus 1, and I want that output. Well, I think it's easy to see. 3/2 minus 1 is 1/2 times 4 is 2 plus 3 is equal to 5. So this new point, and I could probably help my sketch out here by making a better representation. If this guy is 1, I'm coming all the way up here. This is 1, 3. This point right here is 3/2, 5. Okay, and this is, I'm going to label that as my new point. This is my new point. Shorthand there. My new point is 3/2, 5. So what am I going to do? I'm going to create a tangent line 2 using this point. So I want a new tangent line using this point right here. So the new tangent line is going to be the output of the point plus the derivative at this new point. And you should be recalling that when we did this back last semester, that this was pretty straightforward. This was one of the easier topics that we did, so good deal. We need an easy topic right here. Still a topic that definitely needs reviewing. So what do I need to do? I need to figure out what this dude is right here. And what is 5 plus 10/2? 5 plus 10/2, we can do some arithmetic there. 5 plus 3/2, 10/2, that's going to be 13/2. So equation 2 then is going to look like this. This is the second tangent line. It's going to be 5. And all I'm going to do is keep in mind what my derivative is. Let's not lose sight of this derivative. The derivative is always going to be x plus y. I'm using this new point 3/2, 5. Okay. So 3/2 plus 5. 10/2 is going to be 13/2. Let's write that rascal in. X minus 3/2. I don't know what's going on here a minute. I think I'm back. I think I had a moment of lapse there in my video. That's okay. So this is my second tangent line. Okay. What I want to do now, what am I going to do? I'm going to put 2 into that. And that's going to give me my estimation of the y value when x is equal to 2. I could have just used a linear approximation in one tangent line. All Euler's method does is uses multiple tangent lines. So let's evaluate this rascal right here, the second tangent line, at 2. That's going to be 5 plus 13 halves, 2, which is 4 halves, minus 3 halves. Okay. 4 halves minus 3 halves is 1 half, so this is going to be 5 plus 13 halves times 1 half. And that's simply going to be 5 plus 13 fourths. And we can just leave that rascal like that, and that is my estimation. So y is approximately 5 plus 13 fourths when x is equal to 2. What I'd like to do now is switch to the next problem. Let me get this guy over here. Get to my next screen here. Okay, what I'm going to do now is I'm going to show you, we're going to solve a differential equation. We're actually going to solve this dude right here because I can. This is a separable one. I'm going to find y. I'm going to solve the differential equation. This is going to be my initial condition. 2, 1 is on my function. And I'm going to use my y to actually find 3. And then I'm going to use Euler's method to estimate y of 3. All right, so this is a separable differential equation. So let's get to solving this rascal right here. I have this initial condition. It's equal to x, y. This is an easy one to separate. We did some of these. I think this was in December when we did this. So we're going to separate. We're going to put all the y stuff on one side and all of the x stuff on another side. So what I'm going to do is I'm going to divide both sides. And I want the dy on top here. This is my goal. I want the dy on top and the dx on top. So I'm going to multiply both sides by dx. Puts a dx on top. And now I want this x is going to stay here, but I'm going to divide both sides by y, or multiply by 1 over y. And that gets me this. Now I have the differential equation separated. And now what am I going to do? I'm going to integrate both sides. Fairly straightforward. The antiderivative of 1 over y is ln of y, ln of absolute value of y. The antiderivative of x is x squared over 2. And then don't forget the daggone c. And what I'm going to use now is I'm going to use the initial condition of, I believe the initial condition was 2, 1. 2, 1. That's going to make a nice initial condition. I think I wrote the problem to be this way. So I'm going to put 1 in for y. ln of absolute value of 1, 2 in for x, so it's going to be 2 squared over 2. My objective is to find this c right there. And what the heck is ln of 1? ln of 1 is 0. This is 2 plus c is 0. That tells me that c is equal to negative 2. And so now I have this equation here. I have ln of absolute value of y is equal to x squared over 2 minus 2, putting this negative 2 in for this c right there. Now, I still have not solved for y. And if this were an assessment, a formal assessment, you could get many points just stopping here. But we're going to go ahead on. Got a little time on my video. what am I going to do? I'm going to use the definition of logarithms, and I'm going to say, hey, e to the x squared over 2 minus 2 is equal to the absolute value of y, just using the definition of a logarithm. But I notice my initial condition was 2 comma 1. And 1 is positive, so I can write my y this way. And we have to be careful there. I can do away with this because I know the y's are going to be positive. So that's my y. This is my function. And this time, I do have y solved for x, so I can actually call that a function. Not always can I. So this is my function. And if I want to find f of 3, and that was my objective, remember, if I come back here, my objective was to find y of 3. I'm just going to put 3 in for x, and I have e 3 squared over 2 minus 2, and that is going to equal whatever that it is. I think I have that 3 there. Is I think this is a good estimation is 2.1825. Okay, so that's my estimation. What I'm going to do now is I'm going to take that and I'm going to use Eulers method on this particular differential equation, and I'm going to estimate y of 3 using Eulers method. So I'm going to come up with a new slide. Okay, here was my differential equation. xy, my initial condition was 2 comma 1, and I'm going to come up with 2 tangent lines. Tangent line 1, and this time I'm going to start at 2, and I want to end up at 3, and I'm going to use changes of 1/2. I'm going to use Eulers method with 2 steps. So this guy right here, this midpoint is going to be 5/2. 5/2 is the midpoint of 4/2 and 6/2. Okay, and I'm going to stop the first tangent line at 5/2. Tangent line 1 is going to use this point. This is an output here. And right away I know dy dx at 2, 1 is simply going to be 2 times 1, which is 2, times x minus 2. And that's tangent line 1. And what do I want to do? I want to put this 5/2 into this to estimate that point where I'm going to stop at. One plus 2 times 5/2 minus 4/2, which is going to be 5/2 minus 4/2 is 1/2, times 2 is 1. That rascal is going to be 2. So my new point is going to be 5/2 comma 2. And I'm going to use this to create my next tangent line, my second tangent line. Output 2. And the derivative is simply going to be, note, this was an easy derivative, 5/2 times 2 is 5, times x minus 5/2. That's my second tangent line. And what do I want to do? Now, I want to put 3 into that. And that's going to be my estimation for y at 3. 3 plus 5 times 6/2 minus 5/2. 6/2 minus 5/2 is 1/2. So this is going to be 3 plus 5/2. Pardon me, I don't know why I automatically just changed that to 3. That was kind of freaky. So it's going to be 2 plus 5/2, And if I'm not mistaken, 4 halves plus 5 halves is 9 halves. So now I have, using Euler's method, y of 3 is equal to 9 halves. Oh, and that's not a very good estimation. And I believe when I went to my prior slide, the actual y value came out to 12.183, if you will. So this is an estimation of 12.183, which is actually equal to y of 3. And what I want to do is I want to show you graphically with my graphing calculator what's going on here. So I'm going to come up here to my graphing calculator screen, and I'm going to show you, let's pull this rascal out of the way, that in y1 I have the function that I solved. This is the solution to that differential equation. This is the first tangent line. That first tangent line was at the point 2, 1. This is the second tangent line. That tangent line was at 2.5 or 5 halves 2. And so if I'm going to look at this graph. This is the graph, and this is for the red is the first tangent line. So I started at this point right here, 2, 1, and then I went over. This is x equals 2. This is x equals 3. I went over 1 half, and that's where my first tangent line, I stopped it at. And this was the approximation right here. And what did I do at that point? At that point, I created another tangent line using the same slope, the same differential equation, and then I went up to 3. So this value right here of the second tangent line is 4.5, and this guy right here is 12.3. And you could see if I did multiple steps from 2 to 3, say 1/4, I could get this up there much closer. But what Euler's method actually does, it's to sketch the shape of the solution to a differential equation without actually solving that. So, and that's very interesting. Nobody's going to ask you to do that at this level. All they're going to do is ask you to do some maybe 2 steps, possibly 3, at least 2. So, and I can come up here to my table right here and actually see those values. So the function at 2, 1 is where I started. The tangent line is certainly, they're going to meet at 2, 1. This is irrelevant. At 2.5, the original function is 3, but I'm going to use this point 2.52, and the tangent line 2.52 is going to be on that as well. That's where the tangent line, the first tangent line and the second tangent line intersect, is at 2.52. And this is my estimation using Euler's method, and this is the actual value. And no, if you use Euler's method, you're right. I just had a question. If you use Euler's method, you're going to use Euler's method on a function, on a differential equation that you will not be able to solve. This particular example is of a differential equation that you can solve. So when you use Euler's method, it's going to be more like this. I just wanted to throw an example in there. So this is an important video. I went over a little bit over 20 minutes, but this will be a good review of Euler's method and a simple review of solving differential equations. I will bid you goodbye, and we will talk soon.